Yeah, good morning to all. Today we are going to see how we will be coding the assembly language programming which is understandable by the 8086 microprocessor, which we can call as machine coding the programs. In the previous session, we have studied about machine level programs. So what are these machine level programs which are understandable by the machine, which is a low level programs. So in the earlier days, the computer programming were being written in this machine level programming. Later on it went to assembly language, and later on nowadays C, C++, Java, etc. etc. Now what machine coding the programs? So as we all know that uh, we are converting our assembly language instructions into machine codes. So first of all, you should know what is that instruction format is. So as I told you in the previous session, that an instruction can be of 6 byte. Instruction maximum coding will be of 6 byte. In level instruction format, it will be having more than one number of field. Nothing but it will not be having only opcode, it will be having some other operand field or some data in the instruction being present. So basically it will be having more than one number of field. So in the first field, which is always called for the opcode, nothing but operation code field. So what it indicates? It indicates the type of operation to be performed by the CPU. For example, if you write move is a move. What functional it will does? It will does to move the source operand to the destination operand. Second field consists of operand field, which indicates the data field on which the operation by instruction opcode. So as I told you, we will be having a 6 general format of instruction in 8086 instruction set. As we have complex instruction set which is followed by 8086, so we should be able to remember this 6 instruction format of instruction in 8086 instruction format. So length of instruction may vary from 1 byte to 6 byte. So as I told you, two fields, one is opcode field, second one is operand field, and third field can be it might be a data with displacement, whatever. So what this opcode byte means, it tells that the operation to be carried out by the 8086. So format of opcode byte is opcode will be of 6 bits. Opcode for any instruction, opcode field consists of 6 bits. Direction bit will be 1 bit and width 1 bit. So what opcode field indicates? If D is nothing but direction bit, whether the register is a source or a destination register. D is equal to 0 means register is a source register, nothing but we can able to move from register to the memory. Now here register is my source, and when D is equal to 1, we can able to move the data from memory to the register. So nothing but register is the distinction register, whereas W nothing but word or byte. So number of width, how much amount of data, how much amount of bytes or word we are able to communicate, we are able to transfer. If W is equal to 0, it indicates that it will be operates on bytes. If W is equal to 1, it indicates instruction that operates on words. So opcode consists of opcode 6 bits, D bit 1 and W as 1 bit. Totally 8 bits, so 1 byte of instruction. So as I told you, 1 byte instruction, the first instruction format, which is 1 byte instruction, where 6 bits will be coming for opcode and 1 bit for directions, and the one more bit for width bit. Suppose for example, if we have mul bx or return function, these are the example for your 1 byte instruction. Then second one is register to register. So in this instruction you can able to transfer the information from one register to other register. So this format is a 2 byte long. The first one is a 1 byte long. Second type of instruction format is a 2 byte long. The first byte of code consists of opcode of instruction and width of the operand by W bit, right? Second byte of code consists of register and register or memory field. Register or R by M field. Register indicates the name of register, whether it's a source or destination. R by M indicates source or destination operand is located in register. See here. So 6 bits plus one direction bit and one W bit, 1 byte. Second byte consists of direction bit, width bit and register 3 bits, R by M 3 bits. Third, register to or memory with no displacement. So this format is also a 2 byte long, where the first byte of code is same as your register to register format. Second byte of code consists of mod, reg, R by M field. Previously register field 1, 1 for R, D and W, then your reg, then R by M field. Whereas here in the third instruction format, which is register to or memory with no displacement, second byte of code consists of mod, reg, R by M field, where mod indicates whether the displacement is present or not, and if present, which type of displacement, whether it is an 8 bit or 6 bit. See here, when mod is, what mod tells whether displacement is present or not. If it is present, whether it is 8 bit or 16 bit. When mod is 00, it means it doesn't have, the corresponding instruction doesn't have no displacement value. If mod value is 01, it is a low order displacement with a sign extended to 16 bit. Low order displacement, low order 8 bit, low order 8 bit. Low order 8 bit, high order 8 bit, totally 16 bit, but low order displacement with sign extended to 16 bit. 10, low order and high order displacement. 11, R by M field is treated as a register field. So clear with this one. When mod 00, no displacement, 01, low order displacement can be extended to 16 bit. 10, low order and high order displacement, and 11, R by M field is treated as register field. This is how the 2 byte instruction. Next, fourth one is register to or from memory with displacement. This type of instruction format contain 1 or 2 additional bytes for displacement along with 2 bytes of formats. 1 byte if it is 8 bit, 2 bytes if it is 16 bits. So 1 byte for opcode, second byte for mod, reg, r by m, and third byte for lower byte displacement, and fourth byte for higher byte displacement. So in this format, first byte as well as 3 bits from the second byte, which are used for register field in case of register to register, are used for opcode. So in this one, first byte, which is opcode bits, and 3 bits from the second byte, which are used for register field in case of register to register, are used for opcode. Next, fifth one, immediate operand to memory with 16-bit displacement. So this type of instruction requires basically 5 or 6 bytes of coding. The first 2 byte contains the information of opcode, mod, r by m field. Remaining displacement, so it can be a 16-bit displacement with immediate operand. So now we'll see about the registers. We have seen in the previous instruction formats, we have mod, we have reg, and we have r by m. We have seen about mod. When mod 00 no displacement, when mod 01 low order displacement can be extended to 16-bit, when 10 low order and higher order, and when 11 the r by m can be used for register field. Now we'll see the second one, which is reg field, which is of 3 bits. Mod has 2 bits, register has 3 bits. When register is 3 bits, W is equal to 0. So here we need to see about W is equal to 0 also. If it is 0, it is 8-bit, and W is equal to 1 is 16-bit. So when 000 is register code, when W is equal to 0, it will store in AL. When W is equal to 1, it will store in AX. 001, it is for counter CL when W is equal to 0, and when W is equal to 1, CX. 010, it is for data register DL when W is equal to 0, and when W is equal to 1, it is DX. 011, it is base register when W is equal to 0, BL, and W is equal to 1, BX. 100, which is for higher displacements of the same register what we have seen in the previous one. So when it is 0, it is low. When it is 1, it is higher order. AH, CH, DH, BH. But here, when W is equal to 1, it is pointing out to the pointer of the stack, pointer of the base, source index and destination index. It is pointing to the memory segment offset register. Clear with this one? Next. So when mod is equal to 11, we have seen this one. And coming to r by m, yeah. So r by m, 2-bit mod field and 3-bit r by m field together specify the second operand. So this we have seen. Now when mod is equal to 11, when r by m is equal to 000, AL, AX, this is same as your r by m. So if r by m is 000, for mod 00, there is no displacement, fine. It's nothing but your BX plus source index. When mod is equal to 11, nothing but it doesn't have any displacement, but it tells memory mode. It tells memory mode. Whereas 11 register mode. This is what your register mode. Mode was 01, 8-bit displacement, nothing but DH. Mode 10, 16-bit displacement, D16. Like that, we can have BX plus SI, BX plus DI, BP plus SI, BP plus DI. So like this you can able to calculate the effective address of the memory operand. So this is how we'll be calculating the codes for assembly language. For example, if we have move BL comma AL, for example, so opcode for move is 10010. So we'll encode AL. So AL is source operand and BL is destination operand. So AL is nothing but 8-bit. So D is equal to 0, nothing but AL to BL. W is equal to 0 because it is 8 bits, and mod is equal to 11 as it is in register mode, and reg it is code for AL, so 000, and R by M is equal to 011 BL. So total byte is 10000 1000 11 000 011. Total it equal to, in hexadecimal it is 88C3H. So this is how you will be coding the assembly language into machine level.